Hello and welcome to this short video on obtaining the Taylor series of tan inverse x and using it to find pi. So if you haven't seen what Taylor series is, if you don't know, click this video in the top right here and let's continue. To derive this Taylor series of tan inverse x, we're actually not going to be using the Taylor series idea at all. Instead, we're going to be using a different method where we start with some function in a sum of terms and eventually show that tan inverse of x is equal to that set of terms added together. To do this, what we're going to do is start by defining a function. So we'll say let f of t and r, where t and r are two numbers, be equal to negative t squared to the power of r. And we'll say that this is valid for some t and r elements of the real numbers. So t is an element of the real numbers and r is also an element of the real numbers. And when we plug these into this multivariable function f of t and r, it gives us negative t squared to the power of r. Let's now consider a sum of such terms as s of, we'll say s of n and t, which sums a bunch of terms together like r equals 0 up to the value of n, and it will sum a bunch of f of t and r's. So here essentially what we're doing is taking r going from 0 up to n, and for each value of r such as that, we're going to substitute that value of r and some constant value of t into this function and get our answer. And then we're going to do that multiple times, sum all of those values together, and that will be s of n and t. So then here, if I substitute the first function into the second expression, we have that the s of n and t is equal to the sum as r goes from 0 up to n of this stuff here. Substituting it in, we get this is the sum of negative t squared to the power of r. Considering what this sum is, we need to evaluate this thing at r equals 0, r equals 1, r equals 2, r equals 3, and so on. So here if we do that, this is equal to negative t squared to the power of 0 plus negative t squared to the power of 1 plus negative t squared to the power of 2 plus dot 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 all the way up to negative t squared to the power of n. We're going to be writing this in a simpler format, and we're going to be using an identity of geometric series. If we have a geometric series where we're just multiplying each term by a certain amount from the previous term, as in let's say s is equal to, in this case this is 1, so we'll call this 1. The next term is some a, the next term is that thing times itself, so a squared, and then we have a cubed dot 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 all the way up to a certain n number of terms, let's say an. If we have this is what we call a geometric series. Every next term is a certain ratio times the previous term. So here we can see we're multiplying by a, we are multiplying by a again and a again. We can find the sum of this thing easily if we just consider a times that sum. If we consider a times that sum, then every single term here needs to then be multiplied by a. So the first term 1 becomes a, the second term becomes a squared, the third term becomes a cubed, the fourth becomes a to the fourth, and we get dot 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 a bunch of terms until the a n term becomes a n plus 1, and the a n minus 1 term becomes a to the n. So we have all of this. Now we consider subtracting the second equation entirely from the first equation. What we have here is s minus a times s, as in 1 minus a times s, and on the right side this term cancels to this term, so these two cut, these two cut, these two cut, and this occurs all the way down until these terms cut, like the a to the power of n and a to the power of n cut, and on top we are left with just a 1, and on the bottom we are left with a to the power of n plus 1. So here we have 1 minus a to the power of n plus 1. This means that the series sum s is equal to 1 minus a to the power of n plus 1 divided by 1 minus a. Here we have another condition that a should not be equal to 1, because if a is equal to 1, this denominator will be 0. So we do not want that condition to be there. If that condition is there where a is not equal to 1, so we could write say for a not equal to 1, then any series which can be written in this, it can also be written as 1 minus the constant ratio to the power of number of terms plus 1 divided by 1 minus the common ratio. Applying this principle to this series we have over here. Here this first term here is equal to 1. The next term is equal to 1 times this common ratio of negative t squared. The next term is the previous term times that second common ratio of negative t squared, and so on. Therefore, this sum can be written as we go down here, we can see the bottom we have 1 minus a to the power of n plus 1 divided by 1 minus a. So therefore, in this case, since a is negative t squared, we can write that the sum is equal to 1 minus the ratio negative t squared to the power of number of terms plus 1, as in n plus 1, divided by 1 minus the ratio which is negative t squared. So therefore, this sum is equal to this. And here we can see, since we have negative t squared, and we have this thing for t's which are elements of the real numbers, t squared is going to be a positive number or 0 for t element of the real numbers, because no matter what element of the real numbers you have, if you square it, you're guaranteed to get either 0 or a positive number. So therefore, negative t squared is going to be less than or equal to 0 for t element of the real numbers, and therefore negative t squared is not equal to 1 for t element of the real numbers. By this logic, we can say that what we're doing here is valid, because recall, this would not be valid, what we did for the geometric sum would not be valid if the common ratio was equal to 1. Since we can see the common ratio is definitely not equal to 1, there's no problem in doing this. Now what I'm going to do is rewrite this sum as, I'm going to keep the top as it is, as 1 minus t squared negative t squared to the power of n plus 1, but on the bottom I'm going to take this minus and the other minus, cancel them out, and write this as 1 plus t squared. Now what I'm going to do is to break this sum into two. We can see we have a 1 minus a negative t squared to the power of n plus 1, and then divide by a common denominator. I'm going to break it into 2 and write this as 1 divided by 1 plus t squared minus negative t squared to the power of n plus 1 divided by 1 plus t squared. Now what we are going to do is rearrange this to isolate this 1 divided by 1 plus t squared. So here we can see what we got was s of n and t is equal to this whole thing, meaning that 1 divided by 1 plus t squared would be equal to s of n and t plus, because here when we take this to the other side, this minus becomes a plus, plus negative t squared to the power of n plus 1 divided by 1 plus t squared. The next step we are going to do is integrate both of these, but before we do that, we are going to have to define a different variable. Let's define x, and let's say let x be an element of the numbers between negative 1 and 1. If you don't know what this notation is, go check this video on the top right here. If we have this condition, it means that x could be negative 1, x could be 1, or x could be any number in between. Now what we are going to do is integrate both sides of this above expression with respect to t with the limits, and I'm going to choose the limits from 0 up to x. So what we're going to do is take this expression on the top here. I'm actually going to put this definition of x up here so that we can start on the fresh page with our integration. What we're going to do is take this above expression, we'll call it like expression a, and we're going to integrate both sides of a with respect to t from 0 up to x. So what we're going to do is take a, and we're going to integrate the left side from 0 to x, that's 1 divided by 1 plus t squared dt. It's going to be equal to, we're going to do the same thing on the right, the integral from 0 to x of s of n and t plus the negative t squared to the power of n plus 1 divided by 1 plus t squared all dt. Now over here in this expression, on the left hand side, the integral of 1 divided by 1 plus t squared is going to be tan inverse of t. Why? Because the derivative of tan inverse of x is 1 divided by 1 plus x squared. For that same reason, when we integrate it with limits, we're going to have to ignore the constant of integration and just take the limits of both sides. It's going to give us tan inverse of t. So then on the left side, what we have is the tan inverse of t evaluated from 0 to x. And on the right side, I'm going to preserve the integral, but what I'm going to do is split this integral into two pieces because we have a sum of two terms here. I'm going to write this first part as the integral from 0 to x of s of n and t and dt plus the second integral, which is going to be from 0 to x of negative t squared to the power of n plus 1 divided by 1 plus t squared dt. What I'm going to do is call this integral I for now, and we're going to solve it later, but for now we'll just keep it as a symbol as integral I and solve it later. Now what I'm going to do is I'm going to apply the limits to this thing and reintroduce what the summation notation of this sum here is. So introducing the limits here, on the left side, the limits of tan inverse t from t going from 0 to up to x is going to be the tan inverse of x minus the tan inverse of 0. Now here, of course, since tan inverse is valid for any x which is an element of the real numbers, there's not going to be any problems with domains or ranges here. And on the right side, what I'm going to do here for this thing is I'm going to write the integral from 0 to x, and for s of n and t, I'm actually going to substitute the summation notation for s of n and t. S of n and t is this sum right here, so I'm going to bring this sum, I'm going to copy it, bring it down and paste it in replacement of s of n and t. This needs to then be integrated dt, and to that we need to add the integral I. We're going to be solving this later, so don't worry about it. For now I'm going to keep it around as I. Now then, on the left what we have is the tan inverse of x, minus the tan inverse of 0. The tan inverse of 0 is going to be 0, so therefore this is minus 0. This is equal to, and here we have the integral from 0 to x of the sum of terms from r equals 0 up to n of negative t squared to the power of r dt. Now here, since r and t are independent of each other, meaning that no matter what we do to r, t is going to do whatever it does, and no matter what we do to t, r is going to do whatever it does, we can actually swap the integration symbol and the summation symbol, because integrating the sum in this case is the same as summing all of the integrals in this case. It is possible that you change something when you do this thing, but for now, since r and t are independent, we should have no problem swapping these two symbols. Doing so, what we can do is then write this as the sum from r equals 0 up to n of then the integral from 0 to x of each of the terms negative t squared to the power of r dt. And then on the side we need to add the integral I. On the left hand side, tan inverse x minus 0 is just tan inverse x, so we have what we wanted. We have the tan inverse on the left side, and now all we have to do is simplify the right side. On the right side what we have is the sum from r equals 0 up to n of each of these integrals all evaluated and then summed together. So then, what is this going to be? In order to solve this, we are going to distribute this r among this negative 1 and this t squared, because here what we have essentially is negative 1 times t squared to the power of r, which is going to be negative 1 to the power of r times t squared to the power of r. So we're going to do the integral from 0 to x of negative 1 to the power of r, and this t squared to the power of r, using another law of indices, I'm going to write as t to the power of 2r, and then that whole thing dt plus the integral I. Now then, negative 1 to the power of r. Since r is independent of t, taking this thing on the inside of the integral and on the outside of the integral will not have any difference. This is basically a constant with respect to t. Therefore, I can write that the tan inverse of x is equal to the sum from r equals 0 up to n, and I can take this negative 1 to the power of r out of the integral as negative 1 to the power of r, and then we do the integral from 0 to x of what we're left with is t to the 2r dt, and then plus the integral I. Now then, we know how to do this integral here. We know how to do it because, of course, we know that if we have some variable to some integer power, then it's going to give us, like, let's say we have x to the power of n. When we integrate, it's going to be x to the power of n plus 1 over n plus 1. So then, applying this principle to here, we can see that tan inverse of x is going to be equal to the sum from r equals 0 up to n of negative 1 to the power of r times, and on the inside what we have here, t to the 2r is going to turn into t to the 2r plus 1 divide by 2r plus 1, and the limits of integration here are 0 and x, so we have to evaluate this from 0 to x, and to that we need to add the integral I. Now what we're going to do is evaluate these things and leave it as itself and take I separately, solve it and bring it back. So we're going to write that the tan inverse of x is equal to the sum from r equals 0 up to n of negative 1 to the power of r, and then taking this thing, what this thing is going to evaluate to is the first part instead of t we substitute x, so x to the power of 2r plus 1 divided by 2r plus 1 minus the second thing we have to substitute instead of t 0, so we have 0 to the power of 2r plus 1 divided by 2r plus 1. Now here, since r is going from 0 to n, this thing is never going to be equal to 0. However, this thing is always going to be equal to 0. Since the top is always going to be equal to 0 and the bottom is never 0, this whole thing is 0. So we have this thing minus 0, which is just this thing. So then we can rewrite this and write only this part here as the tan inverse of x being equal to the sum from r going from 0 up to n of negative 1 to the power of r times x to the power of 2r plus 1 divided by 2r plus 1 plus the extra integral I. Now we're going to do one more step before we start evaluating things. We're going to take the limit of everything as we take n going to infinity. Now in this case, this thing has no trouble since we don't have any issues where taking n to infinity would cause some issue, and I also does not have any issues where taking n to infinity would cause any kind of issues. We do have this thing that appears to be going to infinity. However, as we'll soon see, this is not an issue because of the range of x we chose. But we don't know that yet, but I'll show you that taking the limit as n approaches infinity is not going to be any form of issue here. So doing that, we can take the limit as n approaches infinity of the left, which is tan inverse of x, is going to be equal to the limit as n approaches infinity of the sum as r goes from 0 up to n of negative 1 to the power of r times x to the power of 2r plus 1 divided by 2r plus 1 plus the limit as n approaches infinity of I. Now then, since here this expression on the inside is independent of n, this is not going to have any kind of consequence as we take the limit as n approaches infinity. Therefore, this left side is still going to be the tan inverse of x. On the right side, however, we're going to keep this thing as is, and we're going to write this as the limit as n approaches infinity of the sum up to n. We're going to write it as the sum up to infinity because that's the only place where we have a dependency. We're going to, instead of having n here, say that since n is tending to infinity, we're summing from r equals 0 up to infinity, and what we're summing is negative 1 to the power of r times x to the power of 2r plus 1 divided by 2r plus 1 and plus the limit as n approaches infinity of the integral I over here. Now what we're going to do is take this thing separately, consider what it's equal to, and replace it back into here. So what I'm going to do is label this equation number 1 and consider I separately. So we're going to consider not just I, we're going to consider the limit as n approaches infinity, and instead of just I, we're going to consider the value of the absolute value of I. The reason I'm doing this is to make things easier. However, we can do it with just I as it is, but I would like to do it with the absolute value of I because it gives us something nice. So then, considering this thing, let's go back up here and see what I was equal to. I is equal to this integral here. I'm going to copy this integral, bring it down, and we're going to replace it and change a few things. So then, writing this down, the limit as n approaches infinity of the absolute value of I is equal to the limit as n approaches infinity, and here we can substitute the value of I in. So substituting the value of I, this is what the value of I is. We have to evaluate the limit as n approaches infinity of the absolute value of this expression over here. So now here we can see some things. Here there's a negative 1 on the inside which we're going to expand out and make things nicer. Doing that, what we have is the limit as n approaches infinity of the absolute value, and here what I'm going to do on the inside of this integral is take this negative 1, write it as negative 1 to the power of n plus 1 times t squared to the power of n plus 1, which I'm actually going to write as t to the 2n plus 2. I can do this, of course, because of the index rules. And then the whole thing here has to divide by 1 plus t squared, and we have to integrate this dt. Now then, since we're integrating with respect to t, and this term here is independent of t, we can actually take it out of the integral. Doing so, we get the limit as n approaches infinity of negative 1 to the power of n plus 1 times the integral from 0 to x of t to the 2n plus 2 divided by 1 plus t squared dt, and then close the absolute value sign. Now then, negative 1 to the power of n plus 1. For integer n's, negative 1 to the power of n plus 1 is going to remain as negative 1 or 1, because if we take negative 1 to an even power to the power of an even number, it's going to be equal to 1, and negative 1 to the power of an odd number is going to be equal to negative 1. And since we're taking the absolute value here, this sign here is going to be destroyed. Whether it's 1, it's going to be destroyed. If it's negative 1, it's going to be destroyed. We're just going to get the actual size of it. So therefore, this thing is redundant. We don't actually need it because we're taking the absolute value. So we can cut this thing out and we can write that this is equal to the limit as n approaches infinity of just the absolute value of the integral from 0 to x of t to the 2n plus 2 divided by 1 plus t squared dt. Now then, here, consider what we have on the inside. We have some real number t to an even power divided by 1 plus t to an even power. This is a positive number and this is a positive number. So therefore we have a positive number divided by 1 plus a positive number, which is a positive number divided by a positive number, which is going to be a positive number. So then this thing is going to be a positive number. However, if x is a negative number, then we will be integrating this thing in the negative direction. Therefore the sum we get is going to be negative. Otherwise, if we do it the other way, we're going to get a positive number. So depending on the sign of x, this integral could either be positive or negative, which means we still need to keep these absolute value signs. However, since we define that x is going to be somewhere between negative 1 and 1 over here, since we define this condition here, we can say that whatever the value we substitute in here, every single value we substitute in is going to be between negative 1 and 1. Therefore, I'm going to put forward this idea. Since the values of x is going to be between negative 1 and 1 inclusive, the values of t that we're going to have here, because here integration is basically just adding a bunch of terms together, well, infinitesimally small terms, but we're still adding a bunch of terms together. In each of these terms, the 1 plus t squared here, the t squared part is going to be between the t part is going to be between negative 1 and 1. Therefore, t squared is going to be less than or equal to 1, and it's also going to be greater than or equal to 0, because when we square this number, which is between negative 1 and 1, the result is going to be between 0 and 1. Therefore, t squared is between 0 and 1. Therefore, 1 plus t squared is going to be between 1 and 2. Therefore, if we consider 1 divided by 1 plus t squared, since 1 plus t squared is between 1 and 2, when we divide 1 by this number, it's going to be some number which is less than or equal to 1. It's also of course going to be greater than or equal to a half. Given this condition, we can now say, since this factor is between half and 1, if we multiply this by this factor by a certain k, let's say k times this thing, k times 1 divided by 1 plus t squared is going to be less than or equal to k. Therefore, this thing here we could say every single t to the power of 2n plus 2 divided by 1 plus t squared is going to be less than or equal to t to the power of 2n plus 2. We're going to use this fact. Since this is true for every single value of k that we could possibly substitute in because of the values of the integrals which we described, due to this fact, we can say that if we integrate each of these terms, then the integral of them is also going to be less than or equal to the total integral that we're considering. Therefore, this sum here is going to be less than or equal to the limit as n goes to infinity of the alternate sum of the integral from 0 to x of just t to the 2n plus 2 dt. This is going to be true because every single term, actually I made a mistake here, this absolute sign needs to be outside here. Anyway, continuing, every single term t to the 2n plus 2 is going to be greater than or equal to every single term here t to the 2n plus 2 divided by 1 plus t squared. Due to that reason, the sum of each of those terms is going to be less than or equal to sum of each of these terms. Now then, let's call this thing j and try to solve j. If we consider j, this integral j is the integral from 0 to x of t to the 2n plus 2 with respect to t. Therefore, here what we have is an integer power of t, which we can then write as t to the 2n plus 2 plus 1, which is going to be t to the 2n plus 3, divide by 2n plus 3, evaluated from 0 to x, which is then going to be equal to x to the 2n plus 3, divide by 2n plus 3, and then minus 0 to the 2n plus 3, divide by 2n plus 3. Now here, since n is tending to infinity, we're never going to have this thing being equal to 0, so that's not an issue. So therefore, this whole term here is 0 to some non-zero power divided by some non-zero value. Therefore, this is going to be equal to 0, which means we can ignore it. Therefore, the value of j is x to the power of 2n plus 3 divided by 2n plus 3. Substituting that in, we can see that the limit over here is going to be less than or equal to this limit, which is going to be equal to this expression here, which I'm going to substitute as the limit, which is going to be equal to the limit as n approaches infinity of the absolute value of x to the power of 2 times n plus 3 divided by 2 times n plus 3. Now then here, since our x is between -1 and 1, x to the power of 2n plus 3 is still going to be between -1 and 1. We don't know exactly whether it's -1 or 1, it depends on n. However, it's going to be between -1 and 1. Therefore, this part here is finite. Because if we take -1, -1 to any power, any even power is going to be equal to 1, and -1 to any odd power is going to be equal to -1. And 1 to any power is going to be equal to 1. Using these two, we can say that whatever here we have on the numerator is going to be between -1 and 1, therefore it is finite. How about the denominator? Well, as n tends to infinity, this thing is going to get really big because there's an n in here. The 2n is going to be really big, and then there's a small plus 3 which we can kind of ignore. So therefore we have some finite value divided by an infinite value. So therefore, this limit here is tending towards 0. Now what we have is that this expression over here, this limit that we initially wanted to find, is less than or equal to this limit, which is itself equal to 0. So therefore we can say that the first limit that we wanted to find, the limit as n approaches infinity of, and actually we can substitute this thing all the way up here. We have all of these equal signs, meaning that that actual limit is the limit as n approaches infinity of the absolute value of I. So therefore the limit as n approaches infinity of the absolute value of I is less than or equal to 0. Now then, here we have an absolute value. If we have an absolute value, this value itself is going to be greater than or equal to 0. So therefore this thing here is greater than or equal to 0. So we can say 0 is less than or equal to the limit as n approaches infinity of the absolute value of I, which is itself going to be less than or equal to 0. We can see here by a theorem which is kind of similar to the sandwich theorem. On the left we have this value here being less than or greater than or equal to 0, and this value is also less than or equal to 0. So therefore this value here must be equal to 0. So therefore the limit as n approaches infinity of the integral's absolute value is going to be equal to 0. So if the absolute value of this thing is equal to 0, then therefore the limit itself must also be equal to 0, because that's the only way that the absolute value of x is equal to 0, if x itself is equal to 0. So therefore we can say that the limit as n approaches infinity of I by itself is also equal to 0. We'll call this statement number 2. We have now proven that that limit, that extra part integral's limit as n approaches infinity, is equal to 0. Let's now combine it with our first expression. Combining it with the first expression, as in we'll say combining 1 and 2, we can say that on 1 what we had was on the left tan inverse x, here we have tan inverse x, so I can write tan inverse x. So tan inverse x equal to, and on the right side what we have is this sum here plus this thing which we now know is equal to 0. So we can ignore it and consider only this sum. So this is the sum from r equals 0 to infinity of negative 1 to the power of r times x to the power of 2r plus 1 divided by 2r plus 1. So we can go down here and write this is the sum from r equals 0 up to infinity of negative 1 to the power of r times x to the power of 2r plus 1 divided by 2r plus 1, and this was convergent for x's between negative 1 and 1. So we can write for x an element of negative 1 to 1. The reason we need this condition is because we assume this condition in order to get to this result. In fact, you can Google this or ask some AI or something if you want. This series is actually non-convergent for x's outside of this range from negative 1 to 1. Within this range it's convergent, and at the endpoints it's also convergent. However, outside of this range it is non-convergent. So therefore we have derived this expression here. This expression is actually the Taylor series of tan inverse x, and we can now use this to find the value of pi. How can we use this to find the value of pi? Well, quite simple. We know that the tangent of pi by 4 radians is equal to 1. Therefore, since pi by 4 is within the range that's valid because we found this thing to be valid for x's between negative 1 and 1, we can say that pi by 4 must be equal to tan inverse of 1. Now then, we have just found the tan inverse of x. We can apply this sum here to the tan inverse of 1 because the tan inverse of 1 is within the valid ranges that are accepted for this summation here. Therefore, I can write that the tan inverse of 1 is equal to the sum from r equals 0 up to infinity of negative 1 to the power of r times, and instead of x here we need to substitute 1. So therefore what we have is 1 to the power of 2r plus 1 divided by 2r plus 1. Now here, since r is an element of the integers, 2r plus 1 over here, 1 to the power of 2r plus 1 is going to be equal to 1. Furthermore, 2r plus 1 here is not going to be equal to 0 because for the valid ranges of r, we cannot have 2r plus 1 equaling 0 because r is an element of the integers. Therefore, pi by 4 must be equal to the sum from r equals 0 up to infinity of negative 1 to the power of r times this thing. This is equal to 1, so we can just write that as 1 divided by 2r plus 1. If we write this sum out, we can see that pi by 4 is equal to, and here what we need to do is send r starting from 0 up to infinity. So we need to substitute r equal to 0 into this expression here, then substitute r equal to 1, then r equal to 2, r equal to 3, and so on. Add all of those terms together, and that is going to be equal to pi by 4. Doing that, when r is equal to 0, we have negative 1 to the power of 0 times 1 divided by 2 times 0 plus 1. And then the next term is going to be when r is equal to 1, so it's going to be negative 1 to the power of 1 times 1 divided by 2 times 1 plus 1. The next term after this is going to be when r equals 2, which is going to be negative 1 to the power of 2 times 1 divided by 2 times 2 plus 1, and so on. If we see what this is equal to, we can see that 2r plus 1 is just the r plus 1th odd number. Therefore, what we have is pi by 4 equal to negative 1 to the power of 0 is 1, and then we have 1 divided by 1. So here we have just 1 plus the next term here is going to be negative 1 times 1 divided by 3. So here we have negative 1 times 1 divided by 3, or negative 1 divided by 3. The next term is going to be positive 1 times 1 divided by 5. So plus 1 divided by 5. The next term is going to be negative 1 divided by 7, and then plus 1 divided by 9, minus 1 divided by 11, and then plus 1 divided by 13, and so on. So therefore, the value of pi is equal to 4 times this infinite sum, which is 1 minus a third plus a fifth minus a seventh minus a seventh plus a ninth minus an 11th, minus an 11th plus a 13th, and then minus a 15th, and so on, minus a 15th, and so on. You might have seen this series elsewhere in some locations, or maybe if you're recreational mathematics enthusiast, you've probably seen this sum. However, you might not know where this comes from. This comes from the tan inverse of x. So now you know how to show the tan inverse of x's Taylor series for x's between -1 and 1, and you also know how to use it in order to find pi. That is going to be all for this video here today, and thank you for watching, and goodbye.